The first speaker of this session is Andreas Hellenbrand, who is going to talk to us about a version of fast and deterministic C-side called D-C-tide. Can we, okay. So it's your floor, 20 minutes of talk.
Thanks for the introduction. So my talk is going to be about D-C-tide, as mentioned, the fast and deterministic version of C-tide. And this is joint work together with Fabio, Michael, and Ryan. And so let's start with the first short introduction of isogenies, so we call what we are talking about. So an isogeny is a non-constant map between two elliptic curves, which is uniquely defined by its kernel. So for some point k on my elliptic curve, I can use this to compute my isogeny or define my isogeny, and then I have the property that the order of my point is equal to the degree of my isogeny. We are working in the C-side setting, so here we have the following C-side isogeny graph. One example prime of the following form. So we have 4 as a cofactor, and then a list of small odd li's, which define my isogeny graph. Here the edges are the supersingular elliptic curves, and the vertices are the isogenies between them. So I have isogenies of degree 3, 5, and 7, which are defined by the prime that I use of this form. And if I now move to this isogeny graph, it's done with something that's called an ideal class group action. If I now want to compute side action, I define a secret key, and in this case, this is a list of exponents in some given range, in this example from -3 to 3. And then the action is just an isogeny chain where I compute a number of 3, 5, and 7 isogenies depending on the secret exponents that I sampled. And here the sign defines the direction in which I do this walk. And each isogeny I compute with something that's called ReLU formula. And the important point here is essentially that the cost of my isogeny depends on my isogeny degree. So the normal case is linear, but there's also a more optimized version where it's the square root of my degree. So here we have a small example for how such a work would look like. For the secret key 2, -3, and -1, I start by computing 3 isogenies in gray, then do 2, 3 isogenies in gray, then I do 3, 5 isogenies in pink, and finally a last 7 isogeny. And this way I can compute my action as this isogeny walk. So the downside of the normal version of C-side is that it's not constant time, because for once we depend on the length of our isogeny walk, so we have a direct dependency on our secret key, and also the isogeny computation itself is depending on the degree. So if we want a constant time version, we need to somehow the length of our walk, and we also need to hide the degree of the isogeny that I compute. And so the idea in C-tide is to group a small Li of the same size into a batch, and then sample one exponent for each Li again, but this time I have a bound per batch that I don't want to exceed. And then to hide the degree of the isogeny, I can use something that's called a Matryoshka isogeny, and here we fill the inner part of this isogeny computation with dummy operations to hide the degree up to the bound of our batch, and so we can hide the degree. So in practice, this would look like something like this. In example here, I have some small ai that I group into 3 batches, and then I also have a batch bound of 3 in this case, and then I can start with sampling a random point, check does it have the correct order for my first batch. In this case, we say it fails, so we simply skip this batch. So the first isogeny I compute, in this case, would be the 11 isogeny, and after that I move to the next batch. After I'm done with the first round, I sample a new point, check again its order, so this time I can compute my 3 isogeny, I can compute my second 11 isogeny, and the last isogeny of the last batch, 29. Do the same thing again, compute my 5 isogeny in the first batch, and so on. But this time, as I only sampled 2 elements from the second batch, I need to somehow still fill this up to height that we only do 2 computations. So I need to compute 119 isogeny as a dummy operation. And then, as in the first round, our point didn't have the correct order, I need to compute the final 5 isogeny. And then I have computed 3 isogenies per batch, all for the same cost. So I have achieved constant time, but obviously this is not dummy free, so we need dummy operations in every case. For the isogeny computation, we have dummy isogenies themselves, and this is also not deterministic, as we need to resample points every round. So another constant time idea is d-seed side, which is a deterministic version of c-side. And here the idea is to only use a unitary exponent. So I only sample an exponent from -1 and 1. So it only defines the direction of the isogeny that I compute. And for this to work, so that I don't have to sample points, I need to compute a single full torsion point that I then can use to compute my complete isogeny in one go. And as we have the property that we compute an isogeny of every degree, we also don't need this Matroska isogeny, so also my isogeny computation is dummy-free. So this gives a deterministic and dummy-free version, but the downside is that it's really slow. So we need to compute 121 isogenies for our smallest key size, and this is already at 7 gigacycle on Skylake CPU. So this is where the idea of our paper comes in. Here the idea is to combine the batching with this unitary exponent. So we get the speed up from having batches and also the dummy freeness from having unitary exponents or the determinism. And this is something, and the system we use for this we call Bombards. It's short for widely overlapping meta batches. So in widely overlapping meta batch is again a set of Li of some size n, and we again have a batch bound m that's smaller than our n. And then we sample mLi out of our set and give each sampled element in direction. And then we can again use this Matroska isogenies to hide the degree of our of the isogeny in our batch. So here again we have an example for this. Here we have following Bombard batch, and we set a batch bound of 5. So we sample 5 random elements from our set, and we see that independently of which element I sample, each will fall in its own sub-batch. And then I can simply compute my 5 isogenies using the Matroska, using the bounds of each of the sub-batches as the bound for my Matroska isogeny. And this way I again hide the isogeny degree and have a constant time implementation. And this comes with quite a nice key space, because we have this nice combinatorial effect of choosing n over m. And then we also have this two-factor because we do the direction for each isogeny again with this -1 and 1 exponent. We can improve on this a little bit, which is what we implemented in this version of the paper, if we allow for dummy isogenies. So we can trade off dummy freeness and having a version with dummies and save some more isogenies because we get an even better combinatorial effect in our key space. So what this allows us to do is make the following observation. Because we have this nice effect, we need way less Li in our prime to achieve the same key space. So we gain some headroom that we can use to speed up our final field arithmetic by increasing the two-factor in our prime. And this way we can improve the Montgomery reduction because our prime is now a little bit more Montgomery friendly. So the goal is then to find the correct trade-off between a fast prime with fast arithmetic and optimal batches, because so we want to find the correct number of Li for some speed up and find the optimal minimum. So we did some greedy search. We tested a different number of Li that we want to use, and then check, okay, what is the speed up that I get for these primes? And we tested this for 226 Li down to 150. And one can see the variation is quite slow, but we still have a local minimum at 205. And if we then apply the speed up that we get for our from our final field arithmetic, we can see, okay, now the new local minimum moves to a prime with less Li. So this indeed has an effect, because now our speed up is at 194. So here are our benchmarks results for this implementation. We have implemented 3 versions. The first one uses the same prime as DC side, so we can make a direct comparison using the same arithmetic. And then the second one is for the lowest number of multiplications, where we use the first greedy result, and then the third one is fine-tuned for cycles. And for this we get about 5 times speed up compared to DC side, which was the main goal of this work. But surprisingly, we are also 17% faster than C-tide, which is a nice result that was not expected by us. However, as you see in this table, while DC side is still dummy-free, our version is only deterministic. However, in our DC type paper, we outlined 2 ideas that can be used to make this algorithm also dummy-free. For this, we need something called taxons, which is short for differential addition chains having unnecessary carries when unneeded for dummy freeness or something like this. But the idea here is that we can compute differential addition chains without dummy operations. And the second idea is to make this Matroska isogeny construct also dummy-free. So we implemented this in some follow-up work that got on uprint just this Saturday. And here we see our speedup is we get a little performance decrease. So we are only 12% slower than the dummy-based DC type version from the last slide, but we are still 4% faster than C-type itself. And we have the same properties than the DC side version. So this time we achieve every property that we want to have. So, yeah, thanks.
His time slot is actually 25 minutes. Like I said, he has 20 minutes of talk, but so we have lots of time for questions. Please, anybody who wants to ask, please come up to the microphone. Okay, well, a question. So, like, as you know, there was some a small controversy considering the parameter sizes of C-side family. Like, originally it was proposed with C-side 512, and as everybody knows who cares about C-side, there was some purported attack using Cooper-Berg's algorithm that supposedly makes it not secure enough. And so as this shows, like this deterministic version is half a second on a Skylake, which is not very useful. Yep. What about 512 bits?
Yeah, good question. The problem here is that we still need a decent amount of Li in our prime to apply this Bombard batching. One can bring this down if one reduces the Tuco factor, but still we would be at around maybe 1500 bit prime. But sadly, this technique is not cannot be used with a 500 bit prime, because there we only have 70 Li to work with, and this is not enough to get this combinatorial effect up to a decent key space. So this is a downside of this, but most of the work focus on this 2000 bit primes at the moment. So we also decided to go with this prime.
I see. So it's not, it's most of what you are doing is so specific to DC type to 2048 that it cannot be used for smaller key sizes.
Yes.
Okay. How badly does it scale if you are forced to go up?
Then it will actually scale better, because we have more Li to work with, and if we move to higher security levels, so this combinatorial effect of our prime, of our Bombard scheme, will have a bigger effect in this case, and we can outperform. We haven't looked at this, but we believe that then the performance gain will be even better than compared to DC side.
Thank you. Still no questions? Okay, well, let's thank Andreas again. Okay, please. We have somewhat of a quandary here. I think, of course, since I'm chairing this session, I think the talks of this session is particularly of interest. So everybody should be here, but they might be like waiting because they thought this starts in 5 minutes or something like that. But in the I think maybe I'm wrong because like given how many people is in the audience right now. Let me first introduce the speaker, and Jesus, Javier, Chi, Dominguez. And unlike most of the current isogeny research, they are using 3 isogeny graph works. And I think let's just turn the floor over to him, and you have plenty of time, but of course don't be too slow.
Yeah, now it's working. It's much better. So this is a collaborative work with a joint work with Eduardo Ochoa Jimenez and Ricardo Neftali Pontaza Rodas. So let's start. So along the talk, I will consider just spline of this particular shape. So it should be congruent with 3 modulo 4. We are working over a super singular elliptic curve with this kind of points, so p plus 1 square or p minus 1 square points over fp square. So in particular, we can think that this is like the quadratic field extension is just like the complex number modulo p, for example. Unless we specify a different model, we are going to assume that it is a Montgomery curve model. What else? A small isogenies, we are assuming that the L is a small integer, in particular 3. We focus on 3, but we compare with 2, which is the state of the art. Yeah, it's kind of slow. We focus on calculation of composition of a small isogenies. As Andrea was saying, an L isogeny is just a homomorphism or between 2 elliptic curves as a groups with a final kernel. In this case, the kernel has size 3 or 2 or in general L. Just focus on composition of n isogenies, and so we start with E0 and we want to compute En, let's say. In particular, we want that you don't have backtracking in the chain. So that means that you don't return back. For example, E1 is not isomorphic to E0, E2 is not isomorphic to E1, and so on. We have an extra additional assumption that let's assume that you have an extra elliptic curve. We call it E minus 1, just for simplicity and for defining the hash function, just called the CLG, the CGL hash function, which is by Charles Goren Lauter. Essentially, you just take a path, you just take a string. In this case, let's assume that it's a binary string, for example, for L equal 2, and then you compute this chain of isogeny. So let's say you have 2 options for E0. You have 3 options essentially. One that corresponds with E minus 1, and the other 2, they are going forward. But we are skipping the branch for E minus 1. And then you repeat the same. Essentially, it's just you take this bit string and then you output the J invariant of the last curve. So I highlight that in this scenario, the elliptic curve is defined over fp squared. That means that the J invariant is over fp squared. So let's go directly with the contribution, and then we explain the applications to the protocols, let's say. So essentially, we focus, we have one contribution that is over fp squared. So the main result is this part, let's say. It's just given an arbitrary elliptic curve, how to determine all the 3 points. So we provide a deterministic algorithm that it returns all of the points. By points, I mean just x coordinates. The y coordinate we excluded, but it's not required for the formulas. Additionally, we improved the mapping that given this Montgomery curve, you map to the friendly model for the 3 isogenies. In particular, in this scenario, the isogenies are calculated by radical calculations. In this case, it's cube root calculations. For 2 isogenous chains, let's say the CGL2, you compute the square roots. You can do it also for 5, 7, so you compute 5th roots, 7th roots, and so on. The other contribution was that we proved that with the previous work, you can compute non-backtracking chain of elliptic curves. We also analyze the case of FP. There are different formulas for that because for efficiently you can do some speed up, let's say. But again, the main result is over the sample of the points. So then a deterministic way. In particular, for this case, we only have 2 options with the x coordinate over FP. For the previous one, we have 4 options. So it's over FP squared. Of course, 2 of them could be over FP. And then we provide and provide optimized efficient formulas without inversion. So it's free inversion, all the formula that we use for both cases. I think that's the summary of the contributions. Let's see how they apply in practice. So there is this scheme encapsulation mechanism proposed by Onuki and Nakagawa. It's called QFESTA. They use very fancy mathematics over the quaternion algebra, but let's focus just on the part that where they need to compute this chain of three isogenies as we are proposing, let's say. Originally, they proposed, well, not so friendly primes. So you can see that they have like 64 times t plus delta bits. The delta is small. Sometimes it's like 3, 4, 5, so it's very small. But it's not friendly for implementations. With the result that we have for all the 3 points, we were able to reduce the size of the price as much as possible without losing security, let's say. It's just the difference is that instead of adding delta, we decrease delta. We highlight that the proposal of QFESTA is completely focused on a very specific shape of primes. So they need this extra factor of 3 in P plus 1. But the result just extend. You can remove just the 3. So either you can have it or you cannot. One can try to find, like, let's say, primes of this with this number of bits, but also including the 3. But then you reach smaller sizes of primes, and therefore you reach lower security levels compared with the ones that we are proposing. What else? That's the highlight. If you have, here we have 1 word less, 164 less word, then you have some speed ups. You have 1 less word, then you reduce amount of bit operations. And in practice, we implement it. So in C code, we verify that it's constant time. By constant time, I mean that the running time of the algorithm is independent from the input, in this case, which is a secret. We found that around between 25% and 35% of savings for this part. These 3 isogeny chains in QFESTA is very demanding task in the protocol. But again, we highlight that this is the first implementation, optimized implementation in C. The original QFESTA only implemented in, I think, Sage and probably Julia, but not in C, let's say, language. The second application is that we try to see how to integrate with the DC type by the talk given by Andreas. We highlight that the proposal by Andreas is completely focused on the group action. That means that it's just in the key derivation. That's, in other words, in the derivation of the secret sharing from the Diffie-Hellman algorithm. We focus here just in the key generation where you need to find this order of this full torsion point. We implemented again. We saw that in average we get 2 times faster. At most we can get 4 times faster compared with DCTI implementation. The main advantage of the result is not because of the formulas, but essentially we also optimize the formulas. But here the formulas are very expensive in the sense that you need a Q-loop. So it's an exponentiation, but in any case we improve it. But the main advantage of the result is that you have a better running time for finding these order 3 points required for the isogeny change. We only need 1 for the radical isogeny, so you only need, for example, you only need 1 order 3 point, and then from that you can do the chain for the isogenies in DCTI and CSI, so over FP. With our results, we were able to just exclude the smallest Li because this is the most problematic part of the protocol in the sense that you need to find a point that if you multiply by P plus 1 divided by 3 is not the infinity point, and then you do the same for 5, 7, and so on. If you remove the tree, you remodify, then you have a better probability to get this full torsion point. Because of that, well, you start giving the advantage of the results for the other 3 points. Also, one interesting point of the result is that you can easily, it's not so straightforward, but you can easily integrate the results to the proposed parameter set from Andreas was saying. You just remove the smaller i's and just increase the number of 3 isoids that you are using. We highlight that finding the optimal parameter sets in this CTI is challenging, so that is because we try to do the less effort to change parameters, and also for having a better comparison in the end. And just some additional remarks. So over FPS squared, let's compare with the state of the art. You have 2 isogenies, which is, let's say, the CGL2 hash function. So in that case, you are computing the square roots per isogeny. Here we don't assume that it's Montgomery friendly. For example, in one paper that or of a VDF that in the next slide you're going to see, you don't have larger order points of 2. For example, you don't have order 8 points, 16 order, so points of order 16 and so on. So you just have 2 order points or 4 order points. So for sure you need to compute in those scenarios the square roots for each isogeny. If you compare with the 3 isogenies, it's just we need to compute cube roots versus square roots, and the difference is not much. So having a speed of in the calculation of cube roots will make more competitive the CGL3, let's say, variant of the half function, and it could be faster. Let's assume if you do it twice as fast, then you're going to be around twice as fast, which will be nice. But this is still an open problem. Also, you can try to integrate these 3 isogenies to a PDF. It was proposed by Rodriguez Enriquez, Chavez Saab, and Tibuchi. They presented in SAC, if I'm not wrong. Essentially, they proposed a PDF over kind of the same property for the primes, but they use this. They propose to use these 2 isogenies that require this square root. So maybe you can use the 3 isogenies, and then you have a better trade-off, smaller, shorter chains of isogenies. It could be interesting to analyze. Also, it could be interesting to see how do you extend this, because if you, in this scenario for 3 isogenies, we have shorter chains. With 5 isogenies, you can have also shorter lengths than 3. So it could be that it will be much faster, even for 7 isogenies. But of course, the bottleneck will become just finding the order 5 points per iteration, so 7 or points of order 7 and so on. So maybe it could be challenging, but it will be, for sure, I will expect that it will be faster than the state of the art, so it could be worth to analyze. I think that's all, so I think I don't have any more to say. Maybe just questions, answer questions, if possible. That was too fast, I guess.
That was fast. So, what is, I mean, so because this is not like a smooth prime, I mean, like where p+1 is not smooth here, right? So, what is the principal use cases of, I mean, which crypto systems?
Yeah, for example, in QFesta, initially we focus on QFesta, and in this case is smooth, the p+1. But they always require to compute this, let's say, long chain of isogeny of degree 3. In that case, well, you cannot avoid to compute the isogeny, the isogeny, without calculating Q groups. So this is the main, let's say, application to a interesting protocol. We highlight that there is no implementation again of QFest over C. We didn't implement it because, well, you need more fancy mathematics. But essentially, this will be one interesting because it's shorter, it's Montgomery friendly, We improve the parameter sets. And in DCTI, the prime is P plus 1 is factorized as 3 times 5 times 7 and so on, all the small small odd prime numbers. And for DCTI, they have a power of 2, so 2 to the something. So they are nice for that one. For the CGL half function, as you highlight, that's the situation. You don't have this friendly, Montgomery-friendly shape. But so you have two options, no? The one that you have very smooth in the P plus 1, but also not so smooth for the P plus 1.
I see. By the way, is anybody who has questions should probably come up to the microphone. But okay, since I don't see any and we have plenty of time, let me ask a stupid question. My life it was in arithmetic as a cryptographer. So could you extrapolate? I mean, so you didn't implement any of this in assembly, and so all of this is probably GMP, right?
No, we use C, and the arithmetic is based on C psi and DC tie and DC psi. So there are some part of assembly for the multiplication and squaring also. It's not taking advantage of the share of the prime, so it could be optimized. So it's as much as optimized as possible, but we don't assume any Montgomery-friendly shape in the, for example, in the arithmetic. So we didn't use GMP. We use pure C, and some part they use assembly code, but they were coming from other contributions from other people, like the authors of CSI, for example.
I see. So, but because the shape of the primes, it is, I mean, it surely can be speeded up.
Yeah.
I mean, do you have any extrapolations on how much that usually is?
Yeah, we have some preliminary comparison we did. We will expect between 10 and 15% of saving. It could be more, depending, because the assembly part code is not the skill of us, let's say, but it could be even 20% of savings. Even, for example, yesterday we have the talk by Zach about our implementation of the auxiliary method. It could be that you just plug this and then you can have it easily implemented in R. So we are just using cube groups. The cube groups operation are using the multiplication addition that we have in assembly in pure C. So it should be not so straightforward, but kind of easy to just plug the optimized implementation from them. And I think they were obtaining like 20%, if I'm not wrong, 15%. So maybe it could be 25% in that scenario, because they explode the share of the prime in the end. So it could be even better in ARM.
Okay, still no questions. Well, I mean, let's thank the speaker again. We are way ahead of schedule as Floyd Zweidinger takes the stage. And of course, I mean, he's going to talk to us about less, and he's,
Yes.
I mean, a very provocative title, less is more.
You will see. It's going to be less.
So I guess, I mean, we are so much off schedule that I think we will just ask him to begin, and you have lots of time
Thank you very much, and I think I will need the time. So yes, this talk is about less is even more, optimizing digital signatures from code equivalence. And this is joint work together with Luke Beckwith, Andre Esser, Edoardo Persicetti, and Paolo Santini. So of course, I'm not saying anything new here. All currently classically deployed cryptography will be broken by a large enough quantum computer soon, TM. We already have multiple post-quantum secure signatures, but we have also an additional call by the NIST to diversify the landscape of signature schemes. And for this reason, we propose LESS. LESS is a CMA secure signature scheme in the ROM, assuming the hardness of the code equivalence problem. Its approach is a zero-knowledge identification scheme, which is then transformed via the Fiat-Shamir transformation into a signature scheme. And LESS can be summarized with the following table. So this table only contains the category 1 parameter sets as well numbers for a highly optimized AVX2 implementation on a Zen 4, so relatively beefy CPU. As you can see, the numbers, the signature sizes ranges from 2.3 kilobytes down to 1.3 kilobytes, and the signing and verifying can be done in around 100 million cycles down to 26 million cycles. And the rest of the talk will be following the title. So first I'm going to talk about what's code equivalence. Next I'm going to tell you the digital signature LESS, how are they computed, what is the zero-knowledge identification scheme. And last but not least, I will be talking a lot about optimizing the scheme to get those numbers. Okay, so what's the linear code equivalence problem? This problem asks to find, given two generator matrices, G and G prime, to find a monomial matrix acting on the rows and a monomial matrix acting on the columns, which puts G and G prime into a linear equivalence. I already added the subscription R and C to highlight whether a matrix is operating on the columns or on the rows. I will slightly reformulate this problem such that the goal is to find a column permutation, a column scaling, such that G is equivalent to the Gaussian elimination of G prime times QC. Right, and with this row reduced echelon form function showing here, I just want to say I apply the Gaussian elimination. Okay, and this linear equivalence problem is actually already around quite some time, for over 30 years. It has attended quite some cryptanalysis, so it's a perfect candidate to be used within a Sigma protocol. And the Sigma protocol looks like this. You have again your two generator matrices, G and G prime, which are, by the way, in systemized form. And you have a secret relation Q among them. Now, the prover samples a random Q tilde and applies it to G to attain G tilde. Now, a verifier could ask, hey, please open this G tilde so I can verify that you know it. Or he could ask to open Q, or to release Q tilde times the inverse of Q, which then would prove the secret knowledge about Q. And this is a complete zero-knowledge Sigma protocol with soundness error 1/2, which means we have to iterate this protocol as usually many times to achieve our wanted security level. And to better understand what's going on there in detail, I'm going to now zoom a little bit into and show you a few details of this protocol. So again, we have our private monomial matrix Q, our two public keys, our public key containing the two matrices, G and G prime. And now the prover, again, as before, samples a Q tilde, commits to it, or more precisely, commits to the hash of G tilde, and then the verifier could ask, hey, please either give me Q tilde or Q tilde times Q. And in either one cases, he can verify that the commitment is correct, either going the way from Q or the way from Q tilde, right? It's exactly as before. This is absolutely perfectly fine. You can apply the Fiat-Shamir transformation, get a signature, and we are good to go. This thing has one big problem, and that's this response. Those are matrices. You don't want to send matrices or don't want to use matrices in your signature. For this reason, it's far too big. And for this reason, in 2022, Xu, Persicetti, and Santini published a paper which changed the Sigma protocol slightly, introducing canonical forms. So what is a canonical form? A canonical form, well, and I highlighted the changes in blue on the slides. A canonical form is a function which computes a canonical representative of a matrix, which is equivalent to the matrix and all its linear transformations. I will explain this in detail in a second, but let me quickly focus on the changes here. So instead of committing on a generator matrix, we are now committing on CF of the non-information set part A of a matrix. This allows us to return in the second case in the response something what I call encode of our monomial matrices, which is just the information set. And now, in the next few minutes, I want to convince you that this equivalence here, so if you compute the canonical form of A hat and canonical form of A, is actually a sane operation. Okay, canonical forms. As I said, a canonical form function CF computes the canonical representative of a matrix A, and this is equivalent to all its linear transformations, which means CF of A is equal to CF of whatever you apply to your A, as long as it's monomial matrices. And the output is also a matrix B, just to clarify this. But how this matrix B actually looks is not important for us. And now I want to show you how these canonical forms are actually computed, or this canonical form function is actually computed, to later show you how to optimize it. And first, we start with a very simple case in which our two monomial matrices here above are just permutations. So we are not scaling whatsoever. We have our two matrices, A and a permuted A, and now you can look for yourself what the permutation is, or I just show you what the steps of this sort CF function is. So first, we want to sort the rows. This is done via a function called sort rows. And then you may think, okay, well, we are lexicographically sorting rows. Closely, we are lexicographically sorting sorted rows. This means we are taking the first row of our permuted matrix and apply whatever sorting function you like and literally sort. And we do this for all rows. So we get this matrix on the right side. And now we sort those rows lexicographically. This means because the third row starts with the 0, 1, it becomes the first, right? Then, and so on and so on. And the resulting permutation is then applied to our original matrix shown here in the middle. And now in the last step, we apply something called sort columns, which literally sorts columns lexicographically. There is no trick. And now you can believe me that if you do this, you will end up in the same matrix, regardless of which path of this algorithm you take, you will end up with the same thing. And it makes actually kind of sense, right? So I give you a list and a permuted list, and now you sort both of the lists, and you will end up with the same sorted result, right? So it makes kind of sense that sorting somehow normalizes permutations. And one little remark here, we see that the result tends to be that zeros or small numbers are shifted to the top left corner of this matrix. This is going to be important in a few slides. In the next step, I want to make the thing a little bit harder, and I allow for scalings on the rows. So we have now, again, our two matrices, but the second one has some scalings, alpha, beta, gamma, applied to the rows. And the idea to remove or to normalize those scalings is to ensure that the sum of each row is run 1. This is achieved by multiplying each row with the inverse of its sum. And then you can see if we do this for both sides, the scalings can be moved out of the sum and they get cancelled out and we receive the same matrix. Now we can again sort and we end up with the same matrices. And now in the last step, we scale the columns. So we additionally allow for scaling in columns. Again, we have these scalings, alpha, beta, gamma. And now the idea is to scale each column by the first element of the first row. This means, again, we multiply this and we get the inverse of this alpha, which can be moved out of this inversion, and they cancel out, and we receive the same matrix. This has one small caveat. It's not unique. So we have the problem that we don't know. We want a unique canonical form at the end. And this is only achieved by iterating this process for all rows. So we once need to need to scale each column by each row. To fully describe the algorithm now once on one slide, we start with our scaled version here on the left side. We first scale each column by the first row. This normalizes, or I say cancel out. It's not canceling directly, but somehow normalizing the scaling on the columns. Next, we normalize the rows, and which like removes or removes the scaling on the rows. And last but not least, we remove the the permutations via sorting via the sort-CF function. And uniqueness is attained via repeating this whole computational process for each scaling in the beginning for each row. And then we take the minimum over the resulting canonical forms, and this is going to be unique. Okay, enough of explaining how this works. Let's go to optimizing the scheme so we can get this faster. And first, I will have a look at the sort-CF function. Remember, this is the example from just a few minutes ago when I said you can sort each row with whatever sorting algorithm you like. No, you just want to compute histograms. It's by far faster. A histogram is simply counting the number of occurrences of each number in a list. So in this case, we have 1, 0, so we put a 1 here, and so on. We repeat this for all rows, and note that this is fully enough information to still be able to compare rows lexicographically. And the result speaks for themselves. This is 2 times faster than a highly optimized AVX2 sorting network for, let's say, 128 elements if your rows have 128 elements. So this is by far much faster, simpler, and comes with a very cool property. It somehow compresses. I know the matrix here doesn't look like it's compressed, but if you have more rows, then your field size has elements. A histogram needs less space than storing the full matrix, which is a nice little feature to decrease the memory consumption of the implementation. Next, I want to have a look into the full canonical form computation and how we can do it faster. And for this, the core idea to optimize this canonical forms computation is to skip over as much computation as possible, for which we know beforehand they will not lead to a shorter canonical form. Right? We are only interested in the end here in the shortest among them. And the trick to skip computation is to first scan the matrix for 2 properties. First, we want to know which rows have no zeros in them, and we store their indices. And next, we want to know how many which rows and their indices have the maximum number of zeros in them. If we are now looking at the first step, the scale columns function, we see that we are multiplying each column with an inverse. And this inverse is obviously not defined if any of those numbers is 0. So we can skip over this whole computation because it's simply not computable. And for this, we can use the Z, which gives us this information. And I know this is a very obvious optimization, but I can assure you that this is not quite obvious to see if you have the full mathematical definition of canonical forms. So it took us quite some time to see this and to be able to skip over those computations. And now in the next step, I want to emphasize what I said, that the sort-CF function here tends to sort the zeros to the top left corner. This means in the first row of each matrix. And with a high probability, the shortest matrix is defined by the shortest first row. right? So whoever has the shortest first row will be the shortest matrix. Well, what's the shortest row? The one with the most zeros, right? So we only focus our computations on those rows which have the maximum numbers of zeros, which are in a ZJ. Note that this only works because the scale columns, scale rows function here does not alter the Hamming weight of an input row. It changes all values, but a 0 will always be a 0, and no other value will be mapped to a 0. And taking this, we see taking these two optimizations, we see an optimization factor of around 60 over a naive implementation of the canonical forms. And this is actually the whole reason why less is even computable in finite time. Now, the next step, remember, we had to iterate our protocol multiple times. So we had to compute the Gaussian elimination of a generator matrix G and multiply it with some monomial matrix Qi multiple times, like 100 times or something. Note that G is already in systemized form, and Qi is basically just a permutation with scaling. So the core idea is to reuse pivot columns over rounds of our zero-knowledge protocol. So let's assume, for example, that our Qi somehow shuffles the second pivot column and the fifth, right, for whatever reason. In this case, we can skip over the very expensive row reduction step by simply swapping the rows 5 and 3 in this case, containing the 5 and the 3, and we are good to go. We don't need to compute the full reduction of the Gaussian elimination. Of course, so in expectation, if this matrix has k rows and 2 k columns, as it's in less, we can skip over k half of its operations, of this expensive row reduction steps. This means in expectation, this would lead to a factor of 2 improvement over all rounds. But obviously, the exact number of such cases depends on the monomial matrix applied. And if we are simply following this, we would lead up with a non-constant time execution, which is bad. For this reason, we are limiting the number of such pivot reusing to some number p, which is smaller than k half. And as long as this number is not overstepped, not so many pivots were reused as this number p, then we are good to go. And this number p is chosen in such a way that in expectation you can sign 2 to the 64 signatures or messages with a single key pair without overstepping this boundary p. Now, I already talked a lot about adding rows, subtracting rows, multiplying, and doing stuff here. It's time to switch from algorithmic improvements to actually implementation improvements. And for this, we have a look at the arithmetic. The prime field in less is 127, and this is a nice prime number with 2 cool properties. The first one is it's only 7 bits long, so we can, whenever we store a number in 1 byte, we have 1 additional bit to handle carries, which is very, very nice. And the next property is that mod 127, 128 is 1. And this is very useful if you have a result of a full multiplication, which is in total 14 bits long. You can compute the modular reduction by simply taking the upper 7 bits, shift them down, and add them to the lower 7 bits. And you're good to go. Not really. There's one caveat. You get this 1 carry bit I just talked about. And now I don't have to tell you there are numerous ways to do this reduction in constant time. But I want to focus here on vectorizing this reduction. So I don't want to compute the reduction for 1 element, but for as many as possible in parallel. And here we see again our x from the previous slide, and I highlighted the carry in red. And if no carry is available, then it's green like here. So the goal is now to compute either x minus q if the highest bit is set, or x, or to compute nothing if the highest bit is 0. I just want to highlight that I said here are 32 lanes. So this is one AVX register, AVX2 register. But what I'm about to show is applicable to ARM Neon, AVX 512, RISC-V vector extension. It's all the same. It's just an example in this case. So, sorry, yeah, again, now we are having this bit dependency selection process between x minus q and x, and in Intel's infinite wisdom, they gave us an instruction for this, which is the vectorized packed blend vectorized byte instruction, which takes 3 inputs, and depending on the third input, it either selects the first one or the second one. So if our mask here is just x, it correctly selects either x and x minus q, and the reduction is performed. Everything is nice, and this step is actually done for 32 numbers in parallel in one cycle. Perfect. But honestly, while implementing this, I was like, okay, this feels like a heavily over-engineered solution to a very simple problem, and it is, because actually you could just use the unsigned minimum instruction, and it would get between x and x minus q, and you would get the same result, but it's slower. For whatever reason, on our test system, the blend instruction is faster than a minimum instruction. But if you are on older hardware, let's say Broadwell, Haswell, or something like this, you should use the minimum instruction as it's faster, or our implementation is using the minimum instruction. Okay, enough optimizations. Let's go to the results. Where does this lead all to? Let us first compare less against itself. On the upper half, you see the original round 1 submission. On the lower half, you see the current state. And if we are now comparing what I call the flagship parameter set, these are the first lines, you see that our signature size got reduced by a factor of 4. And this is fully to the canonical forms, which are so much smaller than previously. And additionally, even though we added computational overhead with all this permutation and stuff I just showed you, and sorting here, sorting there, we managed to get faster by roughly a factor of 2, 2.5 in verifying and signing. And these numbers only get better if we go to the extreme end of our parameter sets, where we only have 1.3 kilobytes of signature size. We can sign in 26 million cycles, and this is an improvement of roughly factor of 8 over the previous submission. So if we already have standards, so we have to compare ourselves against them. So if we compare less against the lithium, you see that we are actually having smaller signature sizes, which is nice. But then the performance numbers, yeah, let's put it this way, less has no chance, and it's far too slow, and especially the public key sizes are tremendous compared to the lithium. So, but if we compare ourselves against Sphinx Plus, we see that less is somehow complementary to Sphinx, right? So in our case, whenever you need small signature sizes, but you can afford for huge public keys, less is the way to go. And let's be honest, in a world where Macaleese is a standard, public key size should not be the problem anymore. So, if we are now comparing ourselves against all other round 2 submissions to the NIST competition, again, this table only shows the category 1 parameter set for a highly optimized AVX2 implementation on the Zen 4 chip. And these schemes are only the ones which are based on a Fiat-Shamir transformation, and only those parameter sets are chosen which are optimized for signature size. And you can see less has the smallest among them, right? Which is very nice already. And even the performance numbers are not completely off, right? We are in the same region with 100 million cycles for Ride or Mirath, and our smallest parameter sets are even competitive with the other ones, except the public key size. And if we are now comparing against the fast sets, so these are the exact same signature schemes, but only those parameters optimized for speed. LES still has the still has the smaller signatures, but the speed now comes a little bit off. And with this, I want to thank you very much, and I'm ready to take your questions.
Anyone who has questions, please come up. I guess so. How likely is it, given that you are working with GF127, like, would you recommend like compressing it in some way, like like radix 127? I mean, presumably when you store it, you compress the bits, right? So 7 bits to...
Yeah, sure. In the signature, we are compressing. Sure. The signature just uses the 7 bits. But while computing, it's very pleasant to have this additional 3 bit there to handle the carries. But for the signature itself, when we are emitting the signature, obviously everything is compressed to 7 bits.
Right, so would it save anything appreciable by like actually computing another compression? I mean, so what the compression you are doing is basically compressing it to 128 from like a byte containing 256. So suppose you actually compress it down to 127, like with arithmetic. I mean, how much does it save, and is that worthwhile?
I don't think. How do you want to compress from 128 to 137? You get 1 additional bit, so you save 1 bit somehow.
No, you don't save 1 bit. I just evaluate a long string of mod 127 as a integer.
Yeah. And how much do you save?
I mean, not that much, but I mean, how much effort would that be?
Not much. I think if I understood you correctly, we are already doing this. The signature is 1 big number, basically.
Okay.
It's 1. So these canonical forms are just 1. They are represented as 1 big number, but when you pass the signature, you split it into bytes.
I see. So it's already done.
Yeah.
Okay. Any other questions? Well, okay, we have lots of time for coffee. Thank the speakers of all 3 of this session, and see you later.